Hey everybody, welcome to the channel. In this video, we're going to be talking about Newton's three laws and how they provide a framework to be able to explain how forces interact with objects in motion and at rest. So let's get to it. First off, the New South Wales syllabus wants you to use Newton's three laws to be able to describe static and dynamic interactions between two or more objects and the changes that result from a contact force and a force mediated by fields. All right, what is Newton's three laws? So here I have a nice textbook definition of Newton's three laws. So his first law is also known as the law of inertia, and you might have learned about these laws in your previous studies in Year 10, but we're going to review them now. So reading this out, quote by quote, an object at rest will continue to remain at rest, and an object in motion will continue with a uniform velocity in a straight line unless it is acted upon by an unbalanced external force. What this means is that whatever your current velocity is, whether that be zero, meaning you're at rest, or you have a particular velocity value, an object with mass will tend to stay in that motion. Okay, so that's Newton's first law. And it's also an expression for equilibrium. So I'm just going to use a blue pen here. And if we were to express this as a mathematical equation, what we're saying is that the net force is equal to zero. So that's saying the sum sigma, the sum of all forces on an object, is equal to zero. And that is an expression for Newton's first law. That's kind of annoying. All right, so Newton's second law is probably his most well-known one because it has a very well-known formula. And basically, quote by quote, what Newton's second law is, it's when an unbalanced external force acts on an object, the resultant acceleration produced is directly proportional to the force and inversely proportional to the mass of the object. Alrighty, so that it's a bit of a mouthful, but if you were to express this as a mathematical equation, which honestly it provides a nice summary for what we're doing, it's sum of F equals to ma. So what this is saying here is that the sum of the forces on the object, an object with mass, that is proportional to the acceleration that's produced. So for example, you have a net force of 1 Newton, and that for a mass that has 1 kilo, that produces an acceleration of 1 meter per second squared. And if you were to double that, you would also double the resultant acceleration for the same mass. Moving on, Newton's third law. Okay, so this time, whenever a body A applies a force on a body B, B applies an equal and opposite force on A. The first force is called the action force, and the second force is called the reaction force. All right, so this introduces the concept we call force pairs. Now, force pairs basically mean that whenever there is one force that comes from object A and acting on object B will introduce a reaction force onto object A of equal magnitude but opposite direction. So the syllabus actually wants you to know this formula. So this is basically a formula that's a summary of Newton's third law. So you might not actually need to use this in a substitution equation or a question that involves mass. But basically what we're saying is force AB is equal to negative force BA. So first off, don't get confused with this notation because it does look like relative velocity, but it's completely different. So what we're saying here is that we're saying the force that comes from object A acting on object B is equal to, in magnitude, the force of object B on object A, but in the opposite direction, hence the negative sign here. All right, so this was just a quick summary, And if you actually notice, there's some similarities between these three equations here. So, well, for the first two anyway, you're talking about summation of forces. In Newton's first law, we're saying that the summation is equal to 0, meaning that there is no net force. In this example, we do have a net force because ma is not equal to 0 in this case. All right, so that was a quick introduction. Let's take this a little bit further by talking about how this explains a mass on the ground. So in this example, we assume this block has a certain mass. So we draw an arrow and we say it has a weight force. And from our studies, we know that weight is mass times gravity. So, whatever the mass it is, say for example, it's 20 kilos, 30 kilos, whatever it may be. G is the acceleration due to gravity. So remember, G is not gravity itself, it's the acceleration due to gravity, and it's measured in meters per second squared. All right, so we know about weight. Now, according to Newton's second law, if we have a net force that goes down this way, then shouldn't this object start accelerating into the ground? That's true, but there is actually another force that acts on the object, and that is the force of the ground on this block. So if I was to draw that force, it would be acting on the object in the opposite direction. So I'll just use a different color. I'll use red. And so I'm going to use the notation N to stand for the normal force. And so I'll just write in brackets normal. So this is the normal force that comes from the ground acting on the object. So this introduces the concept of Newton's third law. So if we imagine the block to be A acting on B, imagine B to be the ground, then that is what the weight force is. It's the force from the object acting on the ground. Then if we imagine FBA, that's the force of the ground acting on the object. However, weight also acts on the main object. So, the block itself, weight will also act on the block, but that's also equal to the force that acts on the ground. So in this example, we have two equal forces, and because they're in opposite directions, if you added W to N, you would get 0. So this means your net force is 0, and that means you will tend to stay at rest. Okay? Because it was previously at rest, it will tend to stay at rest, which comes from Newton's first law about an object with inertia and how its motion tends to stay at its previous state if there's no unbalancing force. Now, let's take this experiment a step further. Imagine, so I'm just going to change to a black pen. Imagine there was a person standing here. And say, for example, this is the size of, the size relative to this person. Imagine this is, say, a train. If this person pushes the train, so the train carriage, imagine it doesn't have wheels, you would think, oh, so he's introducing a force, right? So let's use a different color. Let's use green. So he pushes the train carriage this way. Now, according to Newton's third laws, these two are balanced, so they cancel each other out. And then this force should act as the unbalancing force, correct? So according to Newton's second law, shouldn't this train carriage start accelerating to the right proportional to this force here? Well, the thing is, in an ideal case, when we ignore friction, that would be true. However, from everyday experience, you know that if you push an object that's very, very heavy, whether it be a train carriage, whether it be a truck, a car, any other really heavy object, you by experience know that it doesn't always move, okay? You need to provide a certain amount of force to be able to push something. So what's missing in this model here? What is missing in this conception of our mental framework, our thought experiment? What's missing is friction, as I just mentioned before. So friction is the force. I'll pick a different color again. Well, I'm running out of colors here, so I'm just going to pick black because it's one color I haven't used yet. All right, so I'm going to call this the friction force, and I'm going to call it F, and then subscript F to mean the friction force. Okay, so this friction force, I'm just going to draw it a little bit shorter to be more realistic. Yep. Okay, so this friction force always acts opposite to the intended motion direction. So because this person is trying to push this object to the right, friction will act to the left. Now, friction is an interesting concept, okay? So we're not going to complicate it too much, but you will learn about friction to be equal to mu n. Okay, so this is the basic formula for friction. It's not very complicated, but it might introduce a few concepts you haven't learned before. So this mu character, mu is a Greek letter, just like alpha and beta, and mu is basically some coefficient less than 1, and it's multiplied by n, which we know is the normal force. So what do we know here? Okay, so imagine if an object is heavier, which is part of the weight force, so this weight force, if it's larger, because it doesn't sink into the ground, the normal force acts to balance it, so the normal force will equal to the weight force. And because I'm telling you that friction is equal to this coefficient, which is a constant, it doesn't change. It doesn't change when you're talking about surfaces, so it's the coefficient is based on different things like roughness and the materials that are contacting, but let's not go too deep into it. So if this coefficient is not changing, the only thing that affects friction is n, the normal force. So that means if you were to push on a very heavy object, the friction force has a very large maximum value. Okay, so this explains why the object doesn't move. Now, let me ask you another question. Okay, so I just told you that the friction force is based on the normal force, which is based on weight. So then if I'm saying this, then for example, he's pushing with, say, 20 newtons, okay? But for example, maybe the weight force is 500 newtons. So we're just using example numbers here. And so therefore, the normal force must be 500 newtons. And the friction force, say mu is 0.2, okay? And this has to multiply by n, which we said is 500. And so I'm just going to do some quick maths here. So times 10 will give you 2, and then 2 times 50 will give you 100. So that gives me 100 newtons. Then look at what we have here. We have 20 newtons to the right and a friction force of 100 newtons. So in theory, if we added that up together, if this was positive, plus 20, minus 100, that would give me negative 80, right? Negative 80 newtons to the left. Or, negative 80 newtons implying to the left direction. So intuitively, that doesn't make sense, right? Because if you were to push a very heavy object, the object doesn't just bounce you back due to friction. Okay, so what's wrong here? What's wrong is that friction is a maximum value, okay? So when we calculate friction like this, we're actually saying this is the maximum possible value that friction for these objects can act as. So I'm just going to put a comment here in green. I'm going to say This is the maximum value you can have. So if you apply 20 newtons to the right and the object doesn't move, this means that the friction force only exerts 20 newtons to the left, thereby balancing out the forces, and thereby the object doesn't move. That's how it explains why heavy objects are very difficult to move, and it also explains why the friction force doesn't suddenly bump you back. Alright, so I hope you enjoyed this video. We covered a lot of content here. We covered the Newton's 3 laws. We covered the concepts of equilibrium, which is this case, so there is no net force, so it means it stays at rest because it was previously at rest. We did a little bit of Newton's second law. We used it when doing the weight force here. We also talked about Newton's third law in terms of force pairs, because the weight of the object acting on the ground is equal but opposite to the force of the ground acting on the object. And then we went a little bit further and talked about friction, which is in your syllabus, but it is mentioned in the second submodule, which is forces and energy. So in the next video, we're going to be talking a little bit about how this scenario is present in inclined planes. Thanks for watching. As always, I'll see you for the next video. As always, thanks for watching. This is just to let you know that I help run a Facebook group called Prelim Discussion Group 2018. All you have to do is search for it in the search bar and you'll be able to find it. So it's a good way to connect with your fellow Year 11s, as well as to share resources and talk about the new syllabus. So again, thanks for watching. I'll see you for the next one.